Alright, good morning everyone. Let's get started. So, in the last class we looked at overview of finite difference method. Today we are going to look at finite volume method. Okay. So, that is overview of finite volume method. Okay. So, for diffusion equation, okay. So, essentially we are looking at diffusion equation. Now, again it is a one dimensional diffusion equation. So, I am writing the diffusion equation here as d by dx of gamma d phi dx plus s phi equals 0. Okay. Now, one thing you kind of notice here is that yesterday when I wrote the finite difference method, I wrote the diffusion equation as gamma d square phi by dx square plus some s phi equals 0, whereas today I am kind of purposefully writing in this form, which is what form? Conservative form. Okay, this is a conservative form. Now, of course, these two equations are one and the same if you have gamma as constant. Okay, they are not the same if gamma is not constant, and you would get another term. For example, if you were to write in a non-conservative form, you would get an extra term, right? Extra term, what would that term be? That would be d phi dx times d gamma dx will be there, right? That extra term will be there if you were to write in this form. Okay. Now, having said that, we will not work with the non-conservative form in the finite volume. We will only work with the conservative form as it is written here. We will come back to the discussion on these differences, okay, a little later. When we kind of compare the finite difference and the finite volume methods together. Okay. Now, okay, let's kind of convince ourselves that we want to work with this conservative 1D diffusion equation with a source term, and we want to apply finite volume method. Okay. So, the first step is to basically integrate the governing equation on a control volume. Okay. So, we are going to integrate this. Before that, we need a kind of a control volume. So, what I would do is I would draw a 1D domain. So, that is basically I have some discretization. These are my cells. This is one dimensions. Okay. So, these areas that we have that I am drawing here. So, this is these indicate that the domain is only in the 1D. Okay. The dotted lines indicate that the domain is only in 1D, and we will have a lot of cells like this, right? Just like what we had yesterday in the last lecture for the finite difference method, like we have these vertices. Now, we have some cells here. I would like to call this as a primary cell P. Okay. So, this is a primary cell, okay, which we always indicate with P, and then we call this cell as a cell that is east to the primary cell. We denote with E, and then this cell we denote with W, saying that this is kind of west to the primary cell. Okay. So, we have now 3 cells similar to the I plus 1, I minus 1 that we had yesterday in the finite difference method. Okay. Now, of course, you would have a lot of cells as well, but we would develop the equations for these 3 cells, okay, essentially involving these 3 cells for the primary cell, and see if we can apply the same for each and every cell in the domain. Okay. Now, we also assume that this area vector that we have here, let us say if we say this is x axis, this is y axis, these area vectors are the magnitude of these areas is 1 unit. Okay. So, this is 1 unit. Okay, that is what we assume because this is 1D. It need not be, it could be some area A as well. Okay. Fine. So, if I were to integrate this, and we also say that the domain has a distance, the cell has a width of delta x, and we will also indicate that the distance between the centroids of the primary and the east cell with a little del x E and little del x W. Okay. So, these are the distance between the primary cell centroid and the east cell centroid, and the primary cell centroid and the west cell centroid. Okay. So, we have del x E, del x W and capital del x, capital delta x. These indicate the corresponding distances. Now, of course, if you have a uniform mesh, all these delta x E, delta x W, they are all equal. Okay. If you do not have a uniform mesh, then these are all could be different. Okay. Fine. So, having said this, we will move on to integrate the equation, the governing equation, which is this guy, right. We will integrate this on the control volume. So, that would be integral control volume d by dx of gamma d phi dx dv plus integral control volume s phi dv equals 0. Okay. Why don't I integrate this 0? Won't we get a constant here? If I integrate everything on the left hand side, shouldn't the right hand side become a constant? It should become a constant, isn't it? But I still write it as 0. Is that correct or no? 0 is correct? Not correct. I have integrated the equation, right? But I want to write it as 0. What is the reason? It's a definite integral, right? Okay. So, essentially it is a definite integral. So, we don't have any constants of integration, right. So, the constants of integration are not there. So, because this is a definite integral, as a result 0 remains 0 on the right hand side, okay, because we are integrating on the particular control volume with given extents. Okay, now, okay, I have somehow convinced you and wrote this equation, but this equation is not quite nice, right. This is not what we want to work with. If you want to apply Gauss divergence theorem, this is not how it should look like. So, we will realize that and we will change it. We will change it to control volume. We want to have the del operator, right. So, that is del dot, right, and then this should have ideally be written as I gamma d phi dx dv plus control volume s phi dv equals 0. Now, does it look in a better form, right? Your del dot is I dou x, j dou y and k dou z, and then dotted with I gamma d phi dx, that will give you basically the same thing that we have before. Okay. Now, this is in a nicer form because we want to apply Gauss divergence theorem. Okay. Now, we also realize that for 1D problems, Gauss divergence theorem kind of need not be applied. We could have even get away without applying Gauss divergence theorem. Okay. That we will see in little while. Okay. First, let me apply Gauss divergence theorem and convert the, so essentially use Gauss divergence theorem and convert the volume integrals to surface integrals. Okay. All right. So, I would convert the first term, that is into a controlled surface. What would be Gauss divergence theorem? Del dot a vector dv equals the vector times the area vector, right, a dot product. So, essentially this will be I gamma d phi dx, right, dotted with dA bar is our new term plus integral control volume s phi dv equals 0. Okay. So, this is in a nice form now. Yeah, where in this equation. So, this equation is basically a kind of a scalar equation. I converted it into a vector form, right, with a del dot and I gamma d phi dx, right. This is same as the previous equation. You have I dot I becoming this the same thing, right. I just wrote it in the divergence form, right, that we realize. Okay. Now, we will move on to now what we do is I kind of assume that this gamma d phi dx term that I have remains the same, or I can represent it with so we are essentially what we are doing is we have this control surface. So, what is this control surface? This control surface is nothing but what? This surface and this surface, right. That is what I am integrating. That means I have two surfaces. We will call them this face as little e, okay, that is between the primary cell and the capital E, and we will call this face as little w. Okay. So, these are the faces which we indicate with little e and little w. Okay. Now, we have two control surfaces. We have to evaluate the integral on this integral dA, right, that is basically on this entire face. So, what I assume is that I assume that this value gamma d phi dx can be represented using the centroid value of the face. Okay. So, if I evaluate and I assume that it kind of remains the same. So, I have a face centroid value of gamma d phi dx, and this can be assumed to be a constant, which is the centroid value of the face, and I am going to integrate with that constant value, okay, this entire integration. And we have two such integrations because this is a control surfaces, and those can be now replaced with a summation, right, because I am assuming that these integrations are now over with a constant value, right. So, I can simply write this as this integral I gamma d phi dx dot d, I can simply write it as sum over the faces, that is east face and west face, right, and this integration is on for a constant value. So, this will be gamma d phi dx I gamma d phi dx dot dA bar would be now replaced with A bar, okay, some AF bar, okay, we will see what AF bar is, plus we have this control volume SV dV equals 0, alright. Is everybody okay with this? So, this integration of this value over elemental dA is now replaced with a summation of the total value multiplied with the area, right, dotted with the area. So, this is fine, right, everybody agrees with this? Okay, everybody agrees. Now, what is AF bar? So, AF bar is nothing but F goes from east and west, AF bar would be A east and A west, right. What is A west or A east? 1 unit, and in a vector form this would be I, right, this will be I bar, and A west would be minus I bar, right, minus I cap or minus I bar. Okay, so, we have these two. Now, if I were to dot with these AF bar, what will be the terms? We have I dot I in the when we apply east, and we have I dot minus I when we apply the west phase, right. If I plug in A east and A west into these equations, what we have is we have gamma d phi dx I dot I plus I gamma d phi dx dotted with minus I, right. I have these two terms for the east and the west, okay, where of course, this is evaluated on the east, this is evaluated on the west, right, this entire thing, okay. Plus, now what I introduce another approximation for the calculating the source term. We say that the source term can also be calculated at the centroid of this cell, okay. So, I somehow calculate an average value for the source term at the centroid, okay, and that value prevails over the entire cell, okay, fine. So, I have some average value for the source term which is a representative of the cell centroid value, and that average value prevails over the entire cell. That means that is equal to the integral S phi dV, okay. So, I have some, so I would replace this with S phi bar, which is an average value for the entire cell, times delta V equals 0, okay. I am introducing an approximation here, fine, okay. Now, what is delta V? Delta volume of the cell, that is nothing but 1 times delta x, right. This is the area equals 1 times delta x, okay, fine. So far so good. Now, what we have is I dot I is 1, so you have gamma d phi dx evaluated on the east phase minus gamma d phi dx evaluated on the west phase plus S phi bar times delta x equals 0, okay, fine. So, now we got some statement here which we will come back to it, okay. Now, this, okay, now let us introduce, so the integration is done, then now we introduce a profile assumption for phi, okay. Now, we have these gradients d phi dx and d phi dx on east phase and on west phase. These two have to be somehow linked to the values of phi at the cell centroids, okay. So, for that reason we are introducing a profile assumption for phi. What we say is that we say that phi in the profile assumption, phi varies linearly between P and E and P and W, okay. So, between the cells, the variation of phi, we are saying that it varies linearly, okay. Now, that is an approximation we are now introducing. Just like the approximation we have introduced in calculating the source term, where we said an average value of the source can be found, and which is the value at the centroid multiplied by the volume would give you this integration, okay. That is one assumption, and this is the another assumption where phi is assumed to vary linearly between the cell centroids, okay. Now, you may have a question, okay, why will it vary linearly? It need not vary linearly, but we are going to assume that it varies, saying that the local variation between these cells, if these cells are fine enough, could be represented using a linear variation, okay. Now, if these cells are larger and if there is a nonlinear variation for phi, this will not work correctly, as a result you will get errors, okay. So, fine. Now, with this assumption we can of course calculate the derivatives that we got here, that is gamma d phi dx on the east face. Okay, this is nothing but gamma east d phi dx on the east face. Okay, I can write the diffusion value evaluated on the east face times d phi dx on the east face. Now, because I have introduced a linear profile assumption, d phi dx can be written as phi east minus phi p upon delta x e, right. If you recall what we had was, we had these this is our p, this is our east. Let us say our variation for phi is something like this, right. So, what we have is this distance between these two is del x e, right, and the values are, this is phi east, this is phi p, right. So, we are evaluating the value of the gradient on this east face, right. So, this dou phi dou x on the east face would be phi east minus phi p upon the distance, right, that is del x e. Okay. So, that is what we have introduced. Similarly, I can write gamma west d phi dx west as gamma west d phi dx on the west face would be phi p minus phi west upon delta x w, right, because my I points, my x axis is in the positive, right. So, that is why I get phi p minus phi w by delta x e, right, because delta x has to be measured in the same direction. Okay. Okay, now we have introduced a linear profile assumption for the gradients. So, what we have in a sense done is, we have brought back the value of phi at the cell centroids, right. Now, we have an equation which is which involves phi east, phi p and phi w, right. These are all at the cell centroids. Okay. All right, very good. So, then we will go back to our equation and substitute these things. So, our equation was gamma east d phi dx east minus gamma west d phi dx west plus s phi bar times delta x equals 0. So, I am going to plug in gamma east d phi dx east as phi capital E minus phi p by del x e minus gamma west times phi p minus phi w upon del x w plus s phi bar times del x equals 0. Okay, we got one linear algebraic equation for the cell P. Okay, this is for cell P. I am going to kind of another step would be to kind of rearrange and collect the terms, okay, or collect the terms and rearrange. So, what I am going to do is, there are two coefficients for phi p. So, I am going to send them to the right hand side, okay. That will be gamma east by del x e plus gamma west by del x w. So, if I take this coefficient for phi p and this coefficient for phi p, I can send these two terms to the right hand side. That will give me gamma east by del x w, del x e and gamma west by del x w, right, both on the right hand side with a positive multiplied with phi p equals, we have gamma east by del x e times phi capital E plus gamma west by del x w times phi west plus s phi bar delta x, right. Essentially, this term, the phi w, phi east will remain on the left hand side and the phi p terms go to the right hand side. Okay. So, we have an equation here. We will write in a particular form where we call this coefficient multiplying phi p with the value a. Okay. A is our coefficient, because it is multiplying phi p for primary cell, we call it a p. Okay. Similarly, this coefficient we will like to call it as a sub e, and this coefficient are a sub w. Okay. Now, we will write this equation as a p phi p equals a east phi east plus a west phi west plus s phi bar delta x. Okay. This we can call it as some constant term b. Okay. Fine. So, essentially now we got a linear algebraic equation in terms of phi p, phi east and phi w. Of course, we have assumed that we somehow can calculate the gamma on the faces, right. The gamma diffusion coefficient on the faces can be somehow calculated from its cell values, right. If somebody gives us only description of diffusion coefficient at the cell centers, that is gamma east, gamma west and gamma p, we somehow interpolate and then calculate the values on the faces, because that is what is going into these coefficients of A east, A west and A p, okay. That we have now implicitly assumed, okay. All right. So, if you look at this equation, now we can write one such equation for every cell, right. Okay, let us look at some comments. Okay, so essentially this is, let us say, equation 1, type or equation 1 can be generated for every cell, right, in the domain, okay. Now the entire process has started off with a statement of conservation, okay. So we started off the entire process with a statement of conservation, which is, how do we say it is a statement of conservation? If I go back, remember we had one equation where this one, I say that this is a statement of conservation because what is this term, gamma d phi dx e? So if we define our q bar as what, or q, qx, if I write like this as qx would be what, k dt dx, that is all, with a minus, that is very important, right. So this is qx, this is basically in which direction is this qx going? In the positive x direction, right, that is why it is minus k dt dx. So if I were to write this, if I kind of send this guy to the right hand side, right, this will be what? This will be a minus gamma east d phi dx on the east, this is what? This will be q e, right, some flux that is in the leaving the east face, right, because in the positive x direction. What is this? This will be q west, that is also, it is kind of entering through the west face because it is minus gamma d phi dx. So this is entering through the west face, and so the flux entering through the west face plus we have the source, something is generated, is balancing the flux leaving the east face, okay. This is a statement of conservation, okay. So this is a statement of conservation, right. Of course, this is not new, we have done this before where in general we said if we integrate the governing equation we are going to get a statement of conservation, but we are kind of looking at in a 1D perspective, okay. Okay, so because we have integrated it on a control volume, we ended up with the statement of conservation, okay. And this statement of conservation with profile assumptions, we have arrived at this linear equation, right. This equation is a manifestation of statement of conservation in a linear algebraic form, right. Okay, so that means because it starts with a statement of conservation, the solution obtained using finite volume method is always conservative, okay, always satisfies conservation. Now, okay, we say this thing, that means no matter how coarse the mesh is, the final phi obtained will satisfy conservation, right. For example, if I have a 1D problem, I can take 100 cells, or I could take 5 cells, or I could take 3 cells, right. I can take any number of cells, but every phi that I get for each of these meshes will satisfy conservation, because I am finding phi, essentially I am calculating phi such that it satisfies these statements, right, it satisfies statement of conservation, okay. So that way every phi that we get for any number of cells in the domain always satisfy conservation. Now are those correct, are they accurate? They need not be accurate, okay, but still what you get is a statement of conservation, okay. That is the kind of usefulness of the finite volume method. So, however, the phi may not be accurate. Okay. Essentially, for it to be accurate, you have to take a sufficiently small size cells. Okay. So, that is what so in order to obtain accurate phi, sufficiently small mesh needs to be used. Okay. So, accuracy is not guaranteed, but phi is always satisfies conservation. Okay. But accuracy will be guaranteed if you go for a finer and finer meshes. Okay. Okay, essentially we have the flux balance on the faces is equated by the source term, right. That is what we saw from that conserved equation. Okay. All right. So, now again because we write these things for every cell, we essentially ended up with a set of linear algebraic coupled equations, right, because these are coupled, because whatever is phi east for one cell would be phi p for another cell and phi west for another neighboring cell. Okay. So, these are all coupled. So, essentially we ended up with a system of linear equations, right. Okay. Few more comments, sir. Although finite difference method and finite volume method used different procedures to obtain the system of linear equations, the same solution techniques can be used to solve the resulting system. Okay. So, what we mean is essentially the Ax equal to b that you got, right, or A phi equal to b that we got from finite difference. So, we got some A phi equals b, right. Now, this A is something for finite difference and something else for finite volume method, or it could be the same, we do not know, depends on the particular problem of interest. Okay. Now, this A could be different, but eventually we are casting both of them in A phi equal to b. Okay. So, from here on, if you want to solve, you can have the same solution technique to solve for this linear system of equations. Okay. So, that means if you write one solution technique, that can be used for both finite difference methods and finite volume methods. Okay. You do not need a separate technique as such to solve for this system. Okay. Few more comments. Essentially, the finite difference method is not conservative, whereas the finite volume method is conservative. Okay. Fine, good. Okay. So, one more thing is corresponding to the accuracy. In finite difference method, how do you increase the accuracy of finite difference methods? You have the, of course, the mesh size is there, you make it finer and finer, but does not matter how fine you make it, you have this accuracy is kind of determined by the discretization scheme that you have used, right. So, if we had used let us say a second order truncation error, right, if we have neglected the order delta x square terms, then the finite difference method you got will be second order accurate, right. That means in finite difference method, the accuracy is governed by the number of terms included in the Taylor series expansion, right. Okay. So, essentially Taylor series expansion governs the accuracy. Okay. Now, how would you increase the accuracy in a finite volume method, or which governs the accuracy? The profile assumption, right? Okay, mesh size is something different. We will come back to that. So, one kind of dilemma you probably have is if I take a finer and finer mesh, I am going to get some better solution. That is true, okay? So, that is true, but irrespective of the mesh size that you take, if you have the same mesh size, if you want to increase the accuracy, you can also go for a more terms in your Taylor series expansion, okay, for the same mesh size. So, what we are looking at is in a finite volume method, if you want to change the accuracy, you have to change what will be the counterpart of Taylor series expansion in finite volume method. What we have just made, right? We made some assumptions, profile assumptions, right? We have evaluated the variation of phi as well as variation of source terms, right? So, essentially if you want to change the accuracy for finite volume, you have to change the profile assumptions of phi and the source terms, okay. These have to be changed. If you increase them, you get a better accuracy, okay, higher accuracy. Now, one more thing is the profile assumptions for phi and S phi need not be the same, okay. So, we said phi varies linearly, whereas S phi we said the centroid value will be taken. So, this need not be the same. You can go for a second order, you know, quadratic variation for phi and a constant value for S phi and so on, okay. So, these need not be the same. Okay, questions till now? Yes. Mesh size, yes. Right. Right. So, okay. So, the question is what is the difference between or the relation between mesh size, accuracy and convergence criteria, okay. So, essentially if you have a scheme, okay, the order of accuracy of the scheme is determined with the truncation error you have used, okay. So, the accuracy of a scheme particularly depends on the truncation error, or for example, let us take finite difference method, okay. You have a second order truncation error, as a result your accuracy would be dictated by that, okay, by the second order accuracy. So, now that does not mean that you get a very accurate result, okay. Now, you still have to use smaller and smaller meshes until you get a correct result, okay. Now, and then the convergence criteria is something which is basically tells you that your solution is not changing with time. You probably have obtained some kind of a steady state solution, okay. Now, these things I understand are kind of very confusing. We will, the next part of this lecture is basically looking at that, okay. So, the next discussion will be on accuracy, convergence, stability and consistency, okay. That is what kind of continues after this, because we have now looked at the solution methods. We will also look at these 4 topics. We will not look at the post processing as such at the moment, okay, because yesterday if you go back, we said this chapter is very short. We are getting basically an overview of the numerical method. So, we looked at the finite difference, finite volume, how to integrate, what are the differences. Now, we will look at all these things such as the accuracy and things like that, okay, but we will come back to these things again once we solve for 1D and 2D diffusion equations, okay. Then I think it will be little more clear, fine. No. So, the question is FDM is not conservative. Is that because we have not included the other term, right? Essentially, we took gamma as constant and took it out. Now, this is a good question. It is not because we have taken gamma to be constant, okay. If you had included gamma also as a variable and got 2 terms, right, d gamma dx d phi dx plus gamma times d square phi by dx square. So, if you had solved d gamma dx d phi dx plus gamma times d square phi by dx square plus S phi equals 0, if you had solved this one, this will still come out to be non-conservative, okay. Now, this non-conservativeness or conservativeness also depends on how gamma and SV vary. Okay, if you have a linear problem, most likely is that the solution or the system of linear equations you get, that is the AFE equal to B, that you get from finite difference and finite volume will come out to be the same. If you have a uniform mesh, linear variations for gamma and SV, then finite difference also will start satisfying because AFE equal to B would be the same for both. Okay, but the moment you have nonlinear variations for SV and gamma and you have non-uniform cells, then finite volume method will continue to be a conservative solution, will continue to give conservative solution, whereas finite difference will not. Okay. Now, this will be there in your assignment. Okay. So, I will set up a problem where you would work with both finite difference and finite volume for a 1D system, and you would prove to yourself that it will not be conservative even if I include all these terms. Okay. Of course, if you look at the equations, one thing you can see is that these terms here have only delta x in the denominator, right? Whereas the finite difference methods, we had a 2 gamma by delta x square, right? Why is that? Why is the difference? Taylor series, because we have integrated these equations now, right? We have integrated the equation, so the derivative, order of the derivative has now decreased by 1, right? The d square terms have become d by d, right? D by dx. Because of the integrations, we got rid of 1 delta x there. That is the reason. Okay, now this doesn't matter, even if you can always prove to me that if you have a uniform mesh with constant gamma and 0 source or a constant source, even with this things, you would get the same constant values. The coefficient values will be the same. Okay, that can be proved. Okay, only thing is when you have these nonlinear source terms, diffusion coefficients and non-uniform meshes, you would see that finite difference would not yield a solution that is conservative. Okay, now I am stressing this on the conservative part because that is the strength of the finite volume method. Okay, but it has nothing to do with a statement that finite difference is not correct. Okay, finite difference will also be correct. Only thing is that it will satisfy conservation as a whole in the entire domain. Okay, once you obtain a solution, it will probably be, it will be also conservative. Okay, the solution, final solution obtained, but at different stages, it will not be conservative. Okay, on a cell by cell basis. Fine. So that I think will be clear when we do the assignment problem. Okay. Other questions? No. Okay. Let's move on. So we have few more small things here, which is these kind of definitions, such as what is the accuracy. So we're going to look at what is accuracy, consistency, stability, and convergence. Okay. So these things is what we are going to look at, or we could even, we should also be looking at the solution procedures. Okay. Because we have not discussed, we obtained the AF equal to B, but we did not discuss how do we solve for it. Okay. So I'm going to discuss all of these because there is a question. I thought we will go with this. Okay, maybe we'll go back to first solution procedures and then we'll come back to the accuracy. Fine. Okay, coming to the solution procedures, what we got now is basically A phi equals B, right? We have a system, a matrix which has some coefficients, right, times phi 1, phi 2 and so on, phi n equals something on the right hand side that is known, that is B1, B2 and so on Bn, where n could be the number of cells you have. Okay. Fine. So this is what we have. What would be a typical characteristics of this equation? What will be general features of this equation? General features of this matrix maybe. So if you go back, the equation only connects P to, okay, so we have this equation where the particular P value of the phi is connected to east and west, right? It's only connected to east and west. It is not connected to east of east, right? If I'm at I am only connected to I plus 1 and I minus 1, but not to I plus 2 and I minus 2. Okay, that is of course to do with the linear profile assumption. If I had made a quadratic assumption, I would have gone to east, east, west, west and so on, right? We are not talking about that. Let's say we use linear profile assumption for the entire course. That means we are only connected to our neighbors, I plus 1, I minus 1. As a result, if I were to put as an equation like this, for example, when I write an equation for phi 2, which will correspond to the second row here, I would have some, this is A2 will be there, some coefficient, and I will have some A3, some A1. What will be the connection to phi3 or phi4? 0, right? So, essentially this will be 0, and to all other cells will be zeros, right? Similarly, if you are at phi4, you would have some non-zero value, or phi3, you would have some non-zero value for here, you will have something here, you will have something A4. What will be here? 0. Essentially, you have a lot of zeros, right? So, the matrix is quite sparse, right? So, the matrix is quite sparse. For example, let us say n is there, this is an n by n matrix. So, one of the characteristics is it is a sparse and maybe a banded matrix, right, because you have these diagonals. So, it could be a banded matrix as well, and there are a lot of zeros. Okay, this is a sparse matrix. So, this is one characteristic. Another characteristic is that the coefficients themselves, what we got, okay, these A1, A2, A3 and so on, they themselves may not be fixed for the entire solution process. Okay. For example, if you have non-linearities, then the coefficients of A are updated as you are solving. Okay. For example, gamma, let us say the diffusion coefficient K depends on temperature, you are solving for temperature, K is a function of temperature. With your guessed value of temperature, you obtain some K, right, but then as you keep getting better and better temperatures, the K value gets updated, right. That K value goes into your coefficients AP, AE, A west. Okay. So, that means these coefficients, this matrix itself keeps getting updated if you have non-linearities in the flow problem. Do you see that? So, for example, go back, what is the coefficient we have here? Okay. So, we have here, this is the coefficient, AP contains gamma E, gamma west. If gamma were constant, no problem, everything is constant and you just have A fixed for the entire problem. But gamma, let us say gamma is K, which is a function of temperature. Okay. This, instead of Pp, I am solving for Tp, right. So, as Tp is getting updated in the cells, the particular value of Kt also needs to be updated, right. If Kt is getting updated, your Ap needs to be updated, right. If Ap is getting updated, then your coefficient matrix A, the coefficients are getting changed, right. That means we have to update that. That means these coefficients are only provisional if you have a nonlinear problem. Okay, coefficients are updated. That means these are only coefficients are of A are only provisional. Okay. So, these are the two characteristics that this particular system of linear equations that we obtained shows. Okay. We better make use of those characteristics and tailor our numerical solution techniques to suit those needs. Okay. Thank you.